The AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia, and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.
Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Welcome to today's AI for Manufacturing webinar. My name is Li Hui Wang of KTH, Royal Institute of Technology in Sweden. I'm very honored to moderate this webinar. The topic of today's keynote is breakthrough points for AI in manufacturing. We are fortunate to have Professor Joseph Wanza of Zudaki with us today to talk about this topic. Professor Joseph Wanza is the head of laboratory for engineering and business intelligence at Hanran Research Institute for Computer Science and Control, Zudaki in short, in Budapest, Hungary. His research interest encompasses engineering applications of artificial intelligence, production informatics, cyber-physical production systems, human-robot collaboration, and cooperative and sustainable manufacturing in networks. He has received prestigious honors, including the Knight Cross of the Order of Merit of the Hungarian Republic in 2008, and the Dennis Gaber Prize for Innovation in 2021. He has been involved in university education for decades, teaching at the Faculty of Mechanical Engineering of Budapest University of Technology and Economics. He is a fellow of International Academy for Production Engineering, CIRP, and of the International Academy of Engineering and Technology, AET, and is in the editorial board of some top engineering journals. Ladies and gentlemen, now please join me in welcoming Professor Joseph Wanza to the virtual podium.
Well, Professor Wang, thank you very much for the invitation and the introduction. And I welcome all the participants, and I'm much honored to deliver a presentation here at this respected forum. So my presentation is just starting up. It's still loading. right? So I suppose you can...
Joseph, sorry, we can still see your notes screen now.
Oh, sorry. Then once again, the same happened. This time, I think it will be fine.
Perfect.
All right?
Yes, perfect, Professor.
So my presentation in a nutshell will be about breakthrough points for artificial intelligence in manufacturing. And the story is very long. I try to make it short in an hour or so. And so here you can see the outline of my talk. First, the question is, what is artificial intelligence? This is something that we have to answer. Then I will look back AI and its application in manufacturing because it's a really, really long story. And the CRP in the International Academy of Production Engineering, recently we have made a review of AI tools and techniques and their revival in manufacturing. So I try to summarize some of the results of this work, and then I will discuss these 5 breakthrough points and make 2 conclusions. So here's what is artificial intelligence. So we can think that it is something, or we may say that we are on the threshold of an era which will be strongly influenced and quite possibly dominated by intelligent problem-solving machines, even if we don't really know what intelligence is. Something complex human performances which we happen to respect, but we really don't understand. But we know that it has key elements: search, pattern recognition and classification, problem solving and planning, learning, induction. And we have available techniques as well: heuristics, adaptive self-optimizing mechanisms, classifying systems, Bayesian nets, prediction and expectation models, logic-based inference mechanisms, planner systems, induction mechanisms, discoveries, grammars, efficient encodings. However, all these words were written already more than 60 years ago, actually in 1960 by Marvin Minsky. Each word that I have quoted is from a paper which he submitted under the title Step Towards Artificial Intelligence. So that things that, even though we think about the things in the same way, still a lot of development and research started much, much more earlier. As I see 60 years ago or so. So here is in a single picture the development process, of course, only in a nutshell. So there is an era, pre-AI era, starting in the 40s, as you will see later, and this so-called infancy stage, from which the statements came from Minsky, are in the 60s and then the 70s. And there were 2 winter seasons, if I may say so, of AI, when the exaggerated expectation didn't prove well, and the research pulled back. Nowadays, however, we have seen a very intensive intensification of research thanks to the machine learning techniques, and in particular to deep learning techniques in the recent decade or so. In my presentation, I will show you that there are much more in the background. Of course, we can use these techniques, but we need much more things, and we have much more AI techniques which can be applied in manufacturing. But now the future looks like this, and as far as the process is concerned, I can say that here you can see a kind of model-based trend, and now a data-driven trend, and in manufacturing, the coupling of these 2 trends will be the real resolution. So if we look back AI in manufacturing, we will see that even in the pre-AI era, engineers wanted to use computers, even from creative thinking. This picture is from the late 40s. Still, that time people saw that computers will be very good for engineering practices and even for creative thinking. The development, anyway, led through 2 two threads. One of them was computer science and information technologies, and the other was manufacturing science. And this development was parallel. So along the past decades or so, a kind of parallel development happened, and it was a kind of two-way transfer between manufacturing science and technologies and information sciences on the other hand. This led to so-called cyber-physical production systems. This is what we have nowadays. And at the red line, we start the development of so-called intelligent manufacturing systems. And from that point on, the task of AI was to find an appropriate match between a set of tasks in manufacturing, the available domain knowledge, its applicable representation, and efficient utilization. So we may say from this point on, the efficient use of deficient knowledge was the key issue for AI in manufacturing in many, many branches. This is kind of industrial revolution, the fourth industrial revolution, but this is so-called institutional revolution because it was supported by a lot of projects and a lot of money, of course, in different countries. Here you can see some projects even running in different countries. Especially the whole process started anyway in Germany with the Industry 4.0. But a lot of money was put into development in the USA and China as well, in other countries as well, and all these programs are still running. So it is not finished. This is an unfinished revolution. It's a continuous revolution, which may go to Industry 5.0, but I don't like the time to tell you the truth. Let's stick to Industry 4.0 and see what happens here. And now I will give you a short overview of a review of AI manufacturing in the last 2 decades, but of course I can highlight only some significant developments, typically those where I was participating. And well, here is the storyline. If we look at the last 40 years or so, in production engineering, AI was very, very popular. In the beginning, in the first 2 decades or so, first expert systems, logic-based representation, knowledge representation, then machine learning came into the focus, and then network problems, and nowadays once again learning, machine learning, and of course deep learning techniques populate the landscape of AI in manufacturing. But first, I would like to show you a very, very early attempt. This was made by my colleagues. They tried to match AI tools to engineering requirements in the 80s. That was the time when I started to work in my institute, and this research was anyway executed in my institute. And it was not a simple matching. My colleagues tried to structure and characterize problem domains like design, process planning, production planning, quality control, and so on. Then they started to characterize engineering tasks with time horizon, principle, structure, available knowledge. And then this is the key, they defined generic tasks. And 6 generic tasks were defined altogether: classification, state abstraction, information passing, object synthesis, hypothesis matching, and explanation. And that was the engineering side. And on the tool side, they taxonomized available and emerging AI tools and characterized them. And then they made a mapping via the generic task. So it was not a one-to-one mapping, it was a little bit stepwise mapping. They start to map practical AI problems via the generic tasks to available and emerging AI tools. This was one thing. And through this mapping, they could also show where there are missing points and missing tools. So to the best of my knowledge, this was the first systematic mapping of engineering requirements and AI technologies. But the real breakthrough in my eye was with the rise of the agent paradigm. And with the rise of the rational agent paradigm, which started with the book which was published by Stuart Russell and Peter Norvig about artificial intelligence, a modern approach in 1995. This is the basic textbook knowledge, textbook still for AI education, I think, in thousands of courses around the world. But the basic concept is the following. We have rational autonomous agents which are embedded in an environment. It's very important. They have sensors and actuators, so they can sense the environment and they can have an impact on the environment via their actuators. They have a task to execute and the utility, so we can evaluate anyway by storing the state history and having evaluation functions. We can evaluate the performance of the agent, and the agent has a internal decision mechanism, and its decision is driven by the evaluations. It's going to maximize its utility. The agent may have goals, objectives, and preferences, and of course some prior knowledge. And here the goal is not mimicking human intelligence, but augmenting human intelligence. And this approach is very strongly pragmatic and task-oriented. So here anything may go, really. Either symbolic AI techniques or neural net techniques, doesn't matter. The only thing is that utility should be maximized. So it's a very pragmatic approach. The engineering slide that. And it is very easy to extend, because it's very easy to extend to bounded rationality when the decision mechanism is limited by computational resources. It's very easy to extend towards machine learning, because the performance of task execution can be improved by learning. It's very easy to extend towards robotics, because the agent is embedded in the environment, and this is the essence of robotics, to sense in the environment and modify it via actuators. And it's very easy to extend to multi-agent systems, because the environment can be populated by other agents as well. So in my view, this paradigm was the real breakthrough, the first real breakthrough, when AI techniques could be well applied in manufacturing and especially in production engineering, and which could lead to what we know now, cyber physical production systems. So, and the question is, why is AI interesting for manufacturing now? Well, because it's in a lot of core elements of the digital transformation of the industry. It impacts cyber physical production systems virtually in every segment of the industry. It is also a vehicle to gain new knowledge, to get better understanding, because don't forget that manufacturing systems are one of the most complex human-made systems. So we would like to understand their operation better. We would like to gain knowledge, and the AI can help to get this knowledge. And of course, it has a potential to significantly advance manufacturing as well, because better process control, human-robot collaboration, higher energy and material efficiency, enhanced sustainability, social affluence, all could be improved by the application of AI technologies. So this is all what we consider good. However, for us to be able to do so, we have to resolve some key dilemmas. Because the digitalization of the industry, or the fourth industrial revolution, is driven by some dilemmas, driven by some conflicting opportunities and challenges. On one hand, for instance, we have Internet of Things, a lot of data and the collection of big data. But on the other hand, what we are going to learn should be comply with the available engineering and background knowledge, also managerial knowledge. Communication is possible, is supported by many channels. However, the interpretation of the communicated information, truth and trust are key issues. Openness and sharing of data is possible on the one hand, but privacy, security, safety of data are on the other hand. We would like to have adaptive, robust systems, but still we are engineers, so we are going to optimize. We would like to find the best solution under certain conditions. Near-time responsiveness is a must. So these systems have not too much time to generate responses. You can start a system run during the evening and read the results in the morning. It doesn't work anymore. However, decision complexity is on the other side. Autonomy and emergence are expected properties, but still we would like to have global purposeful behavior. We would like to have systems completing their complex tasks. For instance, we would like to have a production network to make products, even so the partners, the autonomous partners, behave and decide autonomously. Automation and robotics are on the other side, and we like them, and we would like to apply them, but human involvement, collaboration, and also human unemployment are on the other hand. Cooperation and common good are on the one hand, but efficiency, utility, self-interest are on the other hand. All these are conflicting, just like the recent requirements to sustainability and, in the other hand, competitiveness. So I think that these dilemmas arise from the digitalization of the industry. They are some driving forces of the fourth industrial revolution, and the AI can help us to find some resolutions. How? So let's see now what's the case now. Of course, I can very shortly report on that because we don't have too much time, but I would like to show some advancements of AI or advanced technologies of AI in some selected fields. One is, for instance, production system design and planning, because design and planning are always, or were considered always essential signatures of human intelligence. And manufacturing systems and production systems, as I told you, are one of the most complex results of human thinking. And here we have to design complex objects and also the complex web of directions. So we have to design their functions, their structure, and behavior. And on different levels of production, on the levels of machines and processes, on the levels of factories, and on the levels of production networks. Even so, they are embedded in the web of society and nature as well. These problems are not clearly structured, so we have to capture somehow all of the knowledge which are related to these ill-structured problems. And this design should cover or span the whole life cycle of products and production systems. Then we could use them for life cycle assessment, maintenance, and even to reuse, remanufacturing, recycling, which are more and more important. So design synthesis is typically a configuration problem which requires combination and modification with design methods. Never forget, engineers like to reuse earlier solutions. So modification-based design or variant design is a typical thing we are doing. However, for that we have now ontologies which are conceptual structures of a domain. Ontologies are based on consensus. Well, here, for instance, you can see on the left-hand side an ontology of advanced manufacturing, or a part of it, the main concepts. And we have different ontologies for scheduling, steel making, robotic, and so on. And well, the devil is in the consensus. So it's really, really hard to find the consensus. It's really hard to find the common understanding of all the concepts related to a domain. So sometimes we don't do that. Sometimes we rather stick to a core ontology, and then we extend it with specific ontologies related to different domains. But still, an ontology helps you to understand what are the key concepts in a domain, what are their main relationships, what are their main properties. And ontologies help system development because they make the development process much more stable, much more systematized. Ontologies can help machine-to-machine communication, and ontologies can help software development as well. However, we can't capture everything in clear logical terms. For instance, if we take this problem, additive manufacturing, there are a lot of phenomena, for instance, thermal processes, which cannot be captured clearly. So here, data-driven process modeling are also needed, like, for instance, in this picture graph, neural networks are used for capturing the relationship between autonomous manufacturing processes and thermal processes, which are developing the part by building it up. A great result of the industrial transformation or the digital transformation of manufacturing are the so-called digital twins. Digital twins are organized digital models of products and production systems, but they are much more than models because they are mapped with the real system time and again. They are producing digital threads, a lot of data, which later can be used for learning and assessing life cycle properties of the systems. And digital twins follow the product chain, the value chain, and even the asset chain in manufacturing. We have a lot of digital twins, and they have different roles. They can consolidate design decisions from different engineering sources like material, mechanical, electrical control, software engineering. They can support the evaluation of partial and complete design. And of course, they can facilitate all life cycle activities. Digital twins are well-organized models. You can imagine them like an onion, the core of an onion, and all that and layers are put on top of it one by one. So, for instance, here is a real hard engineering problem. As an example, I can show it to you. Welding, robotic welding, where the input is the CAD model of the parts. Here, a door of a car, the fixture, the welding stitches, location, normal vector, then the technological parameters of the welding beam, minimal and maximal focus length, inclination angle, welding times, and so on. We also know the model of the robot and the fixture because, of course, a part must be fixtured, and elements of the work cell. This is the input. And in the end, we have to arrive at a solution which is a complete cell, a work cell model, a complete robot and laser program, which meets all the technological constraints, which is collision-free, which is optimal in terms of cycle time because it's a very, very expensive cell. So here it really matters whether it takes 70 minutes or 80 minutes to make a door. And also you can minimize energy demand anyway if you would like to run, and which is adaptable to weld quality. And all that we are going to do with so-called zero robot programming. And the solution requires the application of a lot of AI technologies, cell design, task sequences, and path planning, search both in the task and the robot configuration spaces for optimized robot program, geometric reasoning, visual weld quality evaluation, and beam control. And all these layers can be put like layers of onion on the core, which is a digital twin. In our case, the digital twin is a linkage model which captures everything in the cell, whether it is static or dynamic, moving or stable. And this linkage model is fit to reality time and again with some tolerance. And here is the result I play you. So in the end, I hope the video will run. Yes. Now here you can see the result. This is a complete work cell. Here you can see the digital twin in the work cell, which is the picture, the workpiece, the robot, the laser beam. You can see the path of the robot as well. And then you will see the physical process. Now we switch to the physical process. There is a real-time interaction between the physical process and the virtual one because the weld quality is controlled by visual recognition. Now it's stopped in my... Sorry, the video, now it's running again. The video is not as good as should be, but we will wait here. Then now, here you can see the laser beam. And then we will switch back to the work cell. So as to arrive at a solution like that, you need in the core a digital twin, and on the top of that, a layer by layer, different functionalities I have shown you. Now let's go to another area, production planning and scheduling. Here we have to decide on strategic or tactical and operational levels how to attain some production goals. And here there are temporary limited actions, but we have to assign to various resources. We have to comply with a lot of constraints on the resources, human resources, machine resources, technological resources. And there are multiple optimization criteria. Costs are, of course, important. Service level is very important. Due date conformance, but emission, energy efficiency are nowadays very important as well. Some of the data are certain, some of them uncertain, like forecasts, and some of them asymmetric. These problems are not always really hard to solve. So that's why AI technologies were invited to solve this problem from the very, very early times. So the problems are in the following. We have to somehow capture all the knowledge which are related to production planning and scheduling problems. Advanced reasoning and search techniques should be applied. Learning is an important thing, especially if the environment is uncertain. And well, multi-agent modeling is also a very important area, because in a production network, all the partners are autonomous. So capturing their behavior is much better in a multi-agent model than in a centralized one. But the key issues are here: representation adequacy, solution quality, and efficiency. And these three are in conflict with each other. Because if you can represent the problem adequately, then you are not able to solve it within short time. If you are representing an approximate problem, then you can maybe you can solve it in a short time, but you don't solve the real problem in that time, and you have to adapt the solution to real circumstances. And it can easily be the case that the solution is not good enough. This is the case anyway for a distributed setting. So here in the representation track, ontologies help a lot. And in my experience, constraint programming is the best technology to capture everything which are related to manufacturing, scheduling. The constraint programming is beyond the classical mathematical programming, and here you can also apply hard and soft constraints. It's important because sometimes if a problem is over-constrained, you need soft constraints or preferences, otherwise you get no solution. And here multiple criteria can also be followed. The problem solving is constraint propagation and search techniques. Here local search techniques can be very well applied. They are really still good. For instance, large neighborhood search are very, very well applicable for solving such constraint problems. However, humans should be involved in the very end of the process. Humans would like to modify the results, so they should be invited into the problem solving process. That's why we call it mixed initiative problem solving. However, here the response time is very, very, very critical. Suppose there is a human operator modifying a schedule. You or the system should give safeguards against violating constraints, and a system should provide a very, very advanced user interface for humans who would like to modify the results without violating the constraints. Sometimes it's harder than to solve the problem anyway. Now, the other thing is that there are a lot of options for learning here. The thing is that better prediction and forecast. Production and scheduling is always driven by future forecast of demand. So better prediction for forecast can always improve. Then model building from event log data. Big data analytics helps here a lot. Collecting data from logs and building up the data model of the factory, like here what we have done for instance for a semiconductor factory is a viable approach. Reinforcement learning is also very well applicable, especially in environments where when we don't know the environment exactly, which is uncertain, and then we can evaluate the action in an environment and then change the policy which is generating actions. We can learn meta heuristics, or we can improve meta heuristics in local search. And we can also learn surrogate models. Sometimes simulation helps a big role in improving heuristics, but we don't have enough time to run a lot of simulation runs. In that cases, so-called surrogate models can be built up, and instead of running simulation models, we can use like a neural net. And here is another thing, multi-agent approaches. They are very intuitive to modeling production planning and scheduling problems in distributed environment. The problem is, however, how to give global warrants, how to give performance guarantees. And there was a trend in manufacturing, holonic manufacturing systems, where such distributed systems work with a touch of centralization and where incentives for cooperation could be given to the agents. And these technologies are coming up again in the new development, which is platform-based manufacturing. Because recently we have witnessed a new development in manufacturing. Production is organized not by direct customer-supplier relationships, but there are a mediator in between them, the so-called manufacturing platforms. Platforms are collecting orders, analyze orders, give some feedbacks to the customers, give a kind of negotiation, and then if the customer says it's okay, then the platform sends the work to some of the suppliers. But the platform can move thousands of suppliers and can connect in that way thousands of suppliers to their customer network. And this is a kind of strange combination of decentralized and centralized manufacturing. The other thing is process modeling and planning. For instance, computer-aided process planning is one of the weakest links in manufacturing automation, because in process planning you have to keep one eye on the world of design and your other eye on the end of production. You have to find bridges or passes from the world of ideas to the world of reality or production. It's very hard to do it automatically. And we try to do process planning in different domains, in machining, sheet metal bending, remote laser bending, mechanical assembly, and in the end we arrived at a solution we think are generic. And this is based on a kind of a three-layered approach. First, we try to analyze the product model and try to identify what are the basic tasks which should be solved. Then we put these basic tasks into a macro planning where the sequence of the tasks and the basic assignment of the tools and resources are solved in a constraint-based model. However, this model is half empty or half ready because there is the danger of over-constraining the problem. Instead of over-constraining it, we generate a high-level plan, and then this high-level plan is given in the phase of micro-planning to different experts. And the different experts analyze the plan, and if they don't find it appropriate, then feed back constraints to the macro-planning, and we reiterate macro-planning again. And we do these iterative planning cycles until we get a solution, which is an executable part program, or there are no solutions. It could be anyway, because if the evaluable tools and techniques cannot solve the problem, then it could be the case. But with this iterative improvement process, we can arrive at a feasible and also close to optimal or optimal plan. Here is a very short example, an assembly planning example. Here we are putting together a resonator, and as you can see, there is no way to use a screwdriver to fix a screw because of the geometric constraints and because of collision. So the heat protector unit on the top was put too early into the part. So what we can do, and actually there is not a single screw, but a set of screws which will be fixed. We can either change the tool to a wrench because it has an access to this screw, or change the sequence. And the tool expert suggests a new constraints, which changes the new constraints in the model, and in that new model, the screens are made earlier, and there is no conflict anymore, and the screws can be fixed by a screw driver as well. And in the end, if we make this whole process, then we get to a feasible and optimal assembly plan. However, there is another approach in process planning. This is the lazy approach, if I may so, which is a variant approach. This is also a very early approach in manufacturing, when we reuse earlier plans. And this is called similarity-based or variant planning. Suppose we have a lot of earlier plans, or earlier with the description of the product. Then we can select one of the earlier ones and adapt it to a new situation. The problem in that case is always to characterize the problems. And here with deep unsupervised learning, for instance, without giving explicit features of the parts, one can set up a connection between part descriptions and plans with a encoder-decoder neural network. And this application has very big potential in platform-based manufacturing, where instant quoting is an issue. So in platform-based manufacturing, you don't have time to make such a detailed planning like I have shown you earlier, and where data are accumulating on the fly. Then another area, big area in manufacturing is process modeling and optimization, especially when there are multi-physics processes, for instance, mental additive processes or forming. And here there are complex relationships between process dynamics and part properties. And these problems are elusive for classical control problems. So here physics-informed machine learning can be applied, special temporal processes can be applied, and deviation from physical equations can also be penalized in a neighbor like that. So we can somehow include existing physical knowledge in these neural network-based models, which is a big step, I think, for combining earlier knowledge with data-driven techniques. Quality control and maintenance is a related field as well. Here, the engineer problems include condition modeling, fault and defective identification, machine tool degradation, and remaining useful life prediction. Here, the problem is that one thing is that, once again, we have non-physical knowledge, but the other thing is that we have very sparse data. Nobody would like to break it too much times. So here, if the data is sparse, then we have to find methods, for instance, data augmentation methods or federated learning methods, to augment data and learn from much more data than we have available in your hands, because otherwise the machine learning techniques are really appropriate to link physical properties with process parameters. And well, now, these are some examples how AI techniques could be applied in manufacturing, but still we are not confident that a real breakthrough happened. We are not confident because there are not too much industrial take-ups of these results. Would we have a lot of take-up, then we would say that breakthrough happened, but it didn't happen yet. And maybe maybe there are reasons why it didn't happen. And I would like to summarize 5 points where I see potential for breakthrough. One is embodied AI and cognitive robotics. So there was embodied AI is about the strong coupling of the physical and software agencies. AI systems have a body and they have a direct connection to the physical world. Look at this example on the right-hand side. Remember the example that I have shown earlier. In my model, all the reasoning happened in the virtual world. In this example, the robot tries to do an action, an assembly action anyway, and when it hits something, then a constraint is generated back to the virtual model. So this is in embodied AI, embodied robotics. Here, perception and action should be coupled in an unstructured environment, and there are more and more co-evolutionary approaches when the physics and the physical and the virtual model are improving together. Here, object recognition techniques based on deep learning, skilled learning techniques based on reinforcement learning are very well applied. And there is a hope that this co-evolution process will develop cognitive faculties like sensory function and fusion, situation recognition, goal setting, risk assessment, and so on. Here's a simple example, for instance, that we have done with our colleagues in Stuttgart from Veripa for learning the skill of putting flexible components into a part. Here, a sensory feedback based on force had to be needed because collision avoidance wouldn't work, because here we have to force collision, but not with too much force. And here, for instance, machine learning based on reinforcement learning was a very good technique to learn the sequence of actions to put a flexible thing into its place. It's very well applicable in manufacturing. The other thing is embodiment. Embodiment has new forms as well. Mixed reality, for instance, is a form of embodiment, when the interesting thing is that we can immerse not only in the present, but we can imagine also in the past and also in the future. The basic of mixed reality is the digital twin. Without that, it is impossible. And there is another track of research, bionic intelligence, which is a tight integration of intelligent technologies and humans, which is a tight integration between nervous system, human body, and external devices. Here, brain robotics, for instance, is a new field. Professor Wang is an expert of that field. Well, then it has some question because one can question whether concepts could be interpreted from EEG signals, which are collected from the brain. But this is a very fruitful or promising direction of research, still open, but we have many, many results in that direction. Exoskeletons are another way for developing bionic intelligence. The second breakthrough point is reasonable and explainable AI. The problem with the brute force learning is that it is untenable, it's unexplainable. Somehow we have to find combined reasoning and learning, and we have to find techniques where we use the existing background knowledge. Engineering has a lot of background knowledge. Somehow we have to comply the learned knowledge together to what we have in our hands. And now here, continuity principle, which is about encoding and processing of information in real numbers, and compositionality principle, where we say that complex information is always enclosed in layer structures which are put together for smaller ones, can be decomposed. So we can go back to the various combinations of neural and symbolic computing. There are many forms of it anyway. And here I can show you one example when the composition principle applied. So we have developed following anyway the AI planning tradition of problem domain description language. Here we have developed a model, a file-level model for task sequence execution and motion planning, where we can describe robotic problems with processes, alternative tasks, motions, and robotic configurations. So we can go down to the very, very low level of robotic programming as well, and solve it with advanced solution techniques. And for instance, what you see on the screen, this visualization was generated, this robotic grinding program was generated by taking this generic approach, which is applicable for robot welding or even for motion, for moving AGVs on the floor. However, but in between, we can learn that the large language models can be applied for learning, for planning. And the essence of planning is changing the verb from the initial state to the goal state. So here we have to keep track of cause and effect relationships without violating the laws of the world during planning. However, large language models are other causal parrots. So they have really amazing approximate retrieval capabilities. But this is something that we take or mistake to faculties of reasoning and planning. But they are language models and not word models. So they can talk causality, but are not causal. They can very well use for generating ideas about how to do some planning task, but they cannot be used for solving planning problems. The third thing is autonomous AI in production. In autonomy, we are replacing systems with humans in different ways. We have different motivations. There are tasks which are not fit for humans. There are tasks which can be done better by machines. There are tasks where we need machines because human expertise is diminishing. And there are tasks which could be solved better by humans and machines. Here you can see in blue overall applications. The challenges are that operations should be solved under conditions which are not predictable. Adaptation should happen in ever-changing conditions. And rich interaction with humans are needed, and we have to warrant safe, trustworthy, and even ethical behavior and improve the performance by learning. We have developed a workflow for solving such problems, which have 5 levels: setting up a model, solving the planning and optimization of the behavior, interacting with the environment, which means also calibration, sensing, and actuating, interacting with other entities like humans as well, and performance improvement. And for instance, in this problem where a generic robotic pick and place problem is solved. You can see the problem, the solution. It goes through a very, very complex solution phase. Both core is still the kinematic digital twin. Remember this onion model that I saw you. And of course, we go through the several levels where we prepare the digital twin, we calculate the stable work hypothesis, we try to plan the grasping, we solve the tolerance analysis problem, then we have to solve the image processing and pose estimation problems, sequence planning, path planning, and execution. All these are followed or solved following the workflow that I have shown you before we can say that we have an autonomous robotic pick and place solution. The first one, and I'm running out of time, so I have to a little bit run up, collective intelligence and teamwork. This is absolutely essential for manufacturing, I think, because collective and group behavior is more than individual behavior. It's a universal property of biological, social, and engineering systems. Its collective behaviors or collective intelligence surpasses individual intelligence. And this is developed among autonomous agents which are diverse and which are decentralized. But teamwork doesn't just happen. It's based on social interactions, shared goals, with interdependencies of workflows. There are different roles and responsibilities, and it needs a kind of shared model of the partners. So here, training and learning is essential. We have to capture basic skills of team working. We have to be able to improve performance, and we have to be able to build up and maintain trust. For instance, a grand challenge for human collaboration is teamwork. On the right-hand side, you can see a kind of classification of robots and humans that we have done earlier with Professor Wang. The real challenge, all of them are challenging, but the big challenge is not one-to-one human-robot collaboration, but human collaboration in teamwork. And I think in the solution of that, digital twins, we say, will have a key role, and where reasonable planning will also have an important role, because all the partners, in a way, should be able to explain their decisions. And for that, we need planning. Well, when it comes to teams, then you can get a mixed system like that. In our laboratories, we are experimenting with systems where we have legacy systems, collaborative systems, the robots and workstations, logistic devices, and we try to set up a mix of systems where collaboration can be experimented with. And the fifth point is trustworthy, ethical, and secure AI. Because there are a lot of challenges, actually 5 challenges AI generates. One thing is that it erodes our self-determination or freedom. It devaluates human skills, it's unemployment. It removes human responsibility, where we say it was generated by the system, it's not my thing. It can also reduce human control, and it can enable human wrongdoing. That's clear thing. So how can we avoid such risk? This is a big problem. And on the hand, there are the security problems as well, which call for solution, but they don't belong to the ethical issues. Even so, we have to solve them. So here we have to identify, like engineers, some ethical principles: transparency and explainability, warranting safety, accountability, fairness and non-discrimination, human control and technology, professional responsibility and promotion of human values. Some of the existing standards explicitly refer to these principles. For instance, the British standard, recent British standard on robotics and human-robot systems. And there are methodologies for developing responsible AI systems when these requirements or ethical principles are explicitly followed. But still, we are on the very beginning of that road. So the question is whether all these developments helped to respond to these dilemmas or not. Can AI help to resolve these issues or not? And well, after this presentation, I think, or I do have, that you will be more optimistic. And once again, let's jump back to the past. Half a century ago, there was the dream of computer-controlled manufacturing. It was a dream that we can completely automatize production. But this dream, that time was also realized that this dream led to nightmares, and the reality was rather in putting human as the most flexible integrator into the core of manufacturing systems. And well, that's happening now because cyber-physical production systems are not the end of the story. We have more and more newer and newer paradigms, for instance, adaptive and cognitive manufacturing system paradigms, or human-centered physical system paradigms. But both of them or all of them put humans into the center of manufacturing. So if I would like to conclude, and I have, then I say that AI contributed essentially to the digital transformation of manufacturing. And in this history, we have used all the armory of artificial intelligence. But AI has to do a lot to the resolution of the key dilemmas. And I think I have identified five breakthrough points where AI can have contributions. All of them put humans into the center, all of them. So this is a positive prospect. And I think these are prerequisites also for the industrial take-up of the results and using AI for the good of manufacturing. So I thank all my colleagues for all these works because I did them with them and for your kind attention. And I am open to questions.
Thank you very much, Joseph. I think you presented a very impressive keynote today. If I may summarize, you talked about the history a little bit back to many years ago and talk about the agent system, multi-agent system, and also talked about AI in design, robotic remote laser welding, in production planning and control, quality control, maintenance, process modeling, and optimization, and provided quite a few examples to walk us through. At the end, you identified 5 breakthrough points. Those are the embedded AI, cognitive robotics, reasonable, explainable AI, autonomous AI in production, collective intelligence and teamwork, trustworthy, ethical, and secure AI. Materials are abundant. It may take some time for the audience to digest. Now I think the online audience can take this opportunity to raise your questions. You can use the chat box to raise your question, and we will organize that during the discussion. So while you are doing your part of work, asking questions, perhaps I can start with a couple of questions from my side, especially talking about the last breakthrough point related to trustworthy, ethical, and secure AI. This is a critical one for most of us. Joseph, as you know, AI has growing very fast and getting stronger and powerful. And some of us may worry about the fact that in the future, not a fact, the potential situation that AI may be getting out of control. So if that's the case, we will be in a very bad situation. So how do you view the AI in the future, despite of different promise in production system? What can we do to mitigate risk?
Thank you for the question. Yeah, as far as production systems are concerned and manufacturing in general, I am not so pessimistic because those AI technologies which are now very broadly applied are covering only one big but still one area of AI applications in manufacturing, and I still think that the declarative methods will remain with us. because declarative methods are also needed by the industrial take-up. So in the industry, people won't use systems whose conditions are not clearly specified. They won't use systems where the basic assumptions are not clearly specified and declared. They won't use systems where there are not guarantees. And the techniques, AI techniques, which are very popular now and that we are afraid of, are not like that. So I don't think that they will go to broad industrial application. They will go to industrial application in conjunction of declarative methods where we have these guarantees. And I do hope that these guarantees will stop the fear on one hand, and will give the guarantees which are needed for ethical AI, which should be always based on transparent behavior, explainable behavior, and in that case, in trust, because trust is the core of things. Trust is the core of the ethical behavior, and if we can have trust in a system, then we can expect that it can behave in an ethical manner as well. So the industrial requirements will stop the proliferation of trust, such techniques which do not arise trust. This is my answer to your question, and that's why I am not so pessimistic about the future, like many colleagues of mine. But that's my personal opinion.
Okay, thank you. Perhaps you can unshare your screen, and the audience can see bigger faces of us. There's another question came in. The standard question also to Professor Wanza: in your model, the human is still playing a central role. In the future, will AI put more people out of work than creating new tasks or jobs?
Well, shortly I refer to ChatGPT when I was speaking about large language models and their application in planning. Because, for instance, because the question arises, if you can generate programs, because you can generate programs with ChatGPT and similar systems, then why couldn't you generate robot programs? Why couldn't you generate, let's say, plans which are executable in a real world? And I try to argue that it won't go, because these models are language models, but they are not word models yet, and they are not linked with the word models. And planning is always about changing the world. If you have an initial state and you have a final state and you have some actions, and you have to put together actions, make a plan of them, which if executed changes the world step by step, without violating the rules, the constraints, the laws of the world. And this is something that cannot be guaranteed by ChatGPT. I tried to generate an assembly plan with ChatGPT, for instance, for this application field that I have shown you before. It was a very clever plan. It was a very nice plan, but it was absolutely generic one. It gave very good ideas what should be considered when you do planning, real planning, but it was not executable plan. They were very good ideas about the environment where a plan should be executed, about what tools could be used for that. But the sophisticated geometric reasoning that I have shown you before, which is essentially, for instance, in assembly planning, cannot be done by a system like that, because they don't know the causal relationships which run or rule the world. That's why some people say that they are causal parrots. On the other hand, such systems are not unuseful in manufacturing. Even in planning, you can generate it you can use it for generating ideas. What I should consider when I solve this planning program? What background information should be available? What I have to think about it? Is something that I have forgotten? We can add the system and it will generate you answers and it will generate you ideas, but you can put into a formalized planning model, but it will never generate you plans unless they are coupled with word models. I don't say it's impossible, but so far they are not coupled. They are only language models, very sophisticated one, but language models. These language models, however, can very well use for a lot of tasks which engineers don't like to do. For instance, consultancy. You have some problems, some people call you or a chat box asks some answer. Most of the answers can be most of the questions can be answered by large language models. The problem is that if the large language model doesn't know where are its limits, and they start to bluff, because that's the problem when it's very hard to distinguish where it's telling something useful and when it's bluffing. And when you use it in consultancy, in a manufacturing application, your customers could be very happy to get very well-polished results right after the questions. But if it turns out that the question is a bluff, then they won't trust it anymore.
You partially answered the second question already. This question is, what do you think of the application perspective of a large language model like ChatGPT in the smart manufacturing domain, especially considering its unpredictability and inaccuracy nature?
I said that since they have no connection with the word models, you can't use them in an environment which are changing. Would they be connected to word models, then it would be another story, we will see. But they are not yet. At least as far I don't know, no application or development about this.
So
there
another
are
question,
attempts.
The following question is, some common problem includes unexpected changes to externally supplied manufacturing materials. With a high complexity comes a higher probability of equipment component failure, and overall clearing a process due to perhaps a common problem like utility, like electricity or cooling water. How can we reduce the impact from such problems? This is not easy to answer question.
Yes, it is. I'm just reading the question. Yes, the adaptive, I have identified 5 breakpoints or breakthrough points, and I think to this question, this adaptive AI is the right answer, where we have to prepare a system to be adaptable to changing conditions. If something doesn't happen as we planned, as we saw during design time, and this is very, very, as far as I see, I have seen you a generic workflow of 5 stages. But going through this 5 staging was very, very different if we did the robotic applications or embedding or grinding or drawing a human face, for instance, by robot, which is also an interesting task anyway. And the big point of difference, we had generic models for the digital twin, we had generic models for planning, but we never had generic models for sensory information processing and actuators. So that was the point when the system met the real world, get information by sensors and change the world by actuators. So that was the point where we needed specialized techniques all the time. Even if the generic model was the same, the planning approach and the optimization was the same. When the reality had to be handled by sensors and actuators, we had to apply and develop specific technologies. So here there was the difference. And here I think there is no generic answer for that. It really task specific. At least so far, there is task specific. In my laboratory anyway, now we are developing a generic tool set for sensory information processing. First, we've concentrated on visual processing, and here we had very, very good techniques. And the visual processing techniques in AI are the best, you know. And you can transform a lot of other physical processing into pictures and then use the well-proven techniques on that. This is something that we do. But force, torque, should also be considered, and the fusion of this information are even much more interesting. But so far, we don't have a uniform set of tools in our hands, and I don't know that anybody has something like that.
The key here is we need to have a closed loop information system and also have an adaptive decision system to handle and plan changes all the time.
Professor Wang is doing that research very intensively. So yes.
So for the online audience, for Charles, if you have follow-up questions, you can raise your follow-up question. And coming back to the trust issue, because the trust is built upon common understanding based on the common ethical standards. AI and human may not have the same ethical standard. We don't have a ISO standard yet. Maybe this is on the development. If AI consider a different ethical perspective than human being, then we may not have trust. So this is a potential issue related to standardization. You mentioned this aspect, but this is also a challenge for the next 5 to 10 years. What do you think about this one?
Yes, it is so, but trust is about keeping promises. So if you consider a teamwork in any setting, trust is that I will do what I promise to do. And then you will trust in me if I do it. And for that, I have to be able myself to form a plan, what to do, and I have to communicate it with you. This is my intention. So what is planning within an agent is intention when you communicate to another agent. And if you keep your actions to your communicated intention or plan, then the other partners will trust you. Otherwise, they won't trust you. And we made experiments with including trust and reputation models into distributed production networks. The reputation is a little bit different. Trust is binary. Reputation is global. In any other web platform, you can see the reputation of the customers and the reputation of the suppliers. So reputation is global. Trust is personal, if I may say so. And considering this extra information and trust and giving a facility or giving a faculty of the partners to evaluate their trust in other partners. The network as a whole operated much better than based on purely, capitalist success or utility-based criteria. So here, on the long term, some partners had an interest to do something against their short-term objectives. And the system as a whole could be driven to cooperative behavior and to do some hard tasks which were not so paying so well than other tasks, if they were taking care of their trust as well. So I think on the long term, trust can add to manufacturing systems, which should be driven towards cooperative systems. And without trust, we can't form cooperative systems.
Thank you. Yeah, this is something we really need to consider. Now we have more questions coming in. You can also check your text box. So I can read this through. Thank you for the clear and just detailed enough introduction to this topic. It has exposed to me connections with the energy sector in which I do research, that we can investigate learnings to potentially implement, explore further, especially in the electricity disruption network level, where AI and even autonomy are not that well progressed yet. Yeah, this seems just a comment.
It is, yes, it is for me too. As I told you, in the factory and production environment, I am not afraid of that model so far because they don't have such properties which are required by real industrial takeout. If they go within the walls of a factory, then it will be another case. But so far, I think industrial take-up requires clear scope, clear assumptions, provable properties, and transparency.
Yeah, because of time, let's go for the last question for today. RAG, retrieval augmented generation, is architecture for building with Gen AI. The nearest system, such as Amazon Q, goes way beyond ChatGPT that you discussed. Future models will be embedded in mobile systems with RAG properties. We should be thinking about these systems, which will be used outside of the scope of the factory. Instead, will be used inside everyone's pocket, critical to think beyond today and rather plan extrapolating to what AI computing infrastructure will enable, both macro, multi-trillion scale LLM in the next 2 to 3 years and nano single trillion scale large language models that will fit on the mobile in 5 to 10 years. Yeah, this is also a comment.
Yes. I agree. This will be the problem, but this is the problem of transparent, explainable AI.
Yeah. Okay. Yeah, because of time, we need to wrap up the webinar for today. Before wrapping up today's webinar, I would like to thank Professor Joseph Wenza again for delivering a wonderful keynote talk today, and also wanted to thank you, the online audience, for listening and participating actively in the discussions. Our next AI for manufacturing webinar will be announced later. Please stay tuned. Have a great day, and bye for now.
And thank you very much for your attention. It was really a big honor to speak to such distinguished forum.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
The The AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia, and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.